Welcome back to this NPT online certification course in molecular rearrangement and reactive intermediates. In the last couple of classes, we are learning about the organolithium. So we have learned in the fourth lecture about the generation of organolithium using the several different strategy. One is the metal halogen exchange, then the transmetallation, and then the deprotonation, and there are several different type of reaction we talk about. In the today's class, I am going to focus on another type of organometallic reagent called the Grignard reagent. So we are going to talk about the generation of Grignard reagent and different type of reactivity. So I am going to talk about the history of the Grignard reagent, how the Grignard reagent was originally synthesized, some of the introduction, trying to focus on the reactivity, then the nature of the Grignard reagent, the effect of the solvent, and the different type of alkyl halides, what will be their effect for the generation of Grignard reagent, and then their structure and mechanism. So Victor Grignard in 1900, okay, so that was the time the work was published, that the generation of Grignard reagent from magnesium and alkyl halide, he can synthesize RMgBr, which was called as a Grignard reagent. So Victor Grignard received Nobel Prize in chemistry in 1912 for this important work, because Grignard reagent was found not only on a particular synthesis of particular molecule, but it has a huge importance in organic synthesis. You will see that it can be used for several different carbon-carbon bond forming reactions. After this, the beginning of this magnesium chemistry, we are going to learn about the reactivity of organomagnesium in compared to the other metal like the lithium, zinc, tin, boron. So first thing, if you see about the magnesium reagent, I think as very similar to the organolithium, what we talk about in the there also there will be a delta minus here, and there will be delta plus on the metal. Okay, so that means you will see, you have already seen in case of organolithium, when you talk about the bonding between the lithium and the carbon, you have seen that the sigma bond electron density is actually on the carbon. That very similar thing happen once you have a magnesium there. Okay, so that means the carbon having the negative charge on it, on the top of it, is kind of acting as a carbon ion. And now if you go in this direction, what we are showing from this particular diagram in below, that once you go in this direction, what we are saying, the increasing difference in electronegativity with carbon. So if you compare the carbon electronegativity with the different type of the tin, zinc, magnesium, lithium, in this direction, what is happening, the difference of electronegativity with carbon is actually getting increased. Okay, so as it is getting increased in this direction, what we are seeing, also we are seeing the percentage of metallic character is increasing, and as well as the polarity. Okay, so that's why you will see that as the organolithium is the strongest one, then organomagnesium, then organozinc, and organotin, and so on. Okay, I think I have talked about this in the organolithium chemistry as well. So now I'm going to talk about how you synthesize it. Suppose I think that is the important thing, because if you are trying to go to the laboratory to to synthesize the Grignard, so then how you do that. Generally you found that we use the magnesium turnings, which mostly are commercially available, or sometimes sometimes this comes in a bigger in size, you have to cut in a small pieces. The next thing is, once you have done that, you have to kind of try to wash this magnesium turning with the dilute HCl, so to clean some of the magnesium oxide which is in the top of this magnesium turnings, because this reaction is some sort of a heterogeneous reaction. It is happening on the surface of the magnesium. So your reagent is mostly this alkyl and aryl halides, correct? So mostly you find the bromides and iodides. Okay, and then you have to use a dry solvent, and that is mostly you use diethyl ether, or THF. Okay, these are the two different solvent. Okay, so diethyl ether or THF, these are the solvent you will find for the generation of Grignard reagent. Okay, and the next thing is, once you are adding this thing together, you are adding this corresponding alkyl halide, and then you are adding the solvent, and you have the corresponding magnesium turnings. Okay, so once you have this reagent, the first thing is the beginning of the reaction is a little bit slower. Okay, because when the reaction is starting, the reaction is slower. So in this time, what is happening, because this reaction initially time is slow, people use some sort of a initiator. We call these are initiator. So there are different type of initiator you can use. One is that you can use 1,2-diiodoethane or 1,2-dibromoethane. Okay, that is one you can use. So you can see these are the 1, 2, or you can have a bromo or you can have a iodo. So why we are using this? Or you can use iodine also as a activator. So these are the things you can use little bit in this mixture, so that can initiate the reaction. How this is happening, we have mentioned here. There is a magnesium oxide layer which can be broken up. Also you can use ultrasound to broken up that layer, or you can use a stirring rod to scratch it, or you can use the few drops of iodine or the 1,2-diiodomethane, sorry 1,2-diiodomethane or 1,2-dibromoethane. So what is going to happen once you react with this with the magnesium? This is going to generate the magnesium bromide or magnesium iodide depending on what you choose, plus you can see you will generate ethylene. So you will see the ethylene will come out. So once you add them, you will see ethylene will come out from the reaction. Okay, that is the time you understand, okay, the reaction already started happening. And very similar thing, once you use iodine also, it is going to clean this magnesium oxide, because it is going to start reacting with the magnesium, forming magnesium iodide. Okay, so that's why these two initiator going to use for this reaction. And once the reaction started, it is going to consume all the alkyl iodide and it is going to convert to the corresponding Grignard reagent. So now, as I mentioned, there is a two different solvent we use. One is the THF, another is ether. And people found out that they can able to what type of coordination is there between this solvent and the Grignard reagent. So it was found that in generally, if you have a THF, then you can see 3 equivalent of THF bound with the magnesium, forming some sort of a pentacoordinated complex. And in case of ether, it could be a monomeric or it could be dimeric. Okay, that means it could have just a one magnesium with 2 ether here, or it could be a 2 magnesium which has a halide with a bridge. So this type of different complex you can find. And not only that, in the particular reaction when you are forming the Grignard reagent, it has a slink. I am going to come back to that discussion in a minute. So first we are going to learn the mechanism. Okay, what is happening once you add this alkyl halide with the magnesium turnings. So this reaction actually goes via a single electron transfer mechanism, ACT. So you might see sometime the question come, what is the mechanism, how the Grignard reagent was synthesized. It's called single electron transfer. So I think I have already taught you guys some of the single electron transfer event. If you remember when I was talking about this Barge reduction and acylon condensation, I talk about some of this. So here you can see here what is happening. You have a magnesium. So magnesium can give a single electron to the alkyl halide to form this Rx dot minus. Now there will be, and then there will be magnesium plus. Now there will be a homolytic cleavage between this R and X to generate R dot and X minus. I think you can understand this nicely. Then R dot is going to react with this Mg magnesium dot to form Rmg plus, and you have the X minus. So that can form Rmgx. So literally what is happening, something like you have Rx and the magnesium kind of got inserted between the R and X to form Rmgx, correct? So now as I was telling you at the beginning, that once you have this, once you try to mix this alkyl halide and this corresponding the magnesium turning, it's not only going to form Rmgx, it can form mixture of couple of things. We call it as a Sleng equilibrium. So it is kind of, we call it a Sleng equilibrium. So it was found out that depending on the R group, whatever R you are using, whatever alkyl halide using, it's a primary, secondary, tertiary, you find there will be different equilibrium. That means the equilibrium of formation of R2Mg. So that is also present in the reaction. Okay, once you mix them. So that ratio, this equilibrium depends on the size of the R group. It can also form something like that, which actually associated with a halogen bridge. Okay, so there are two Grignard reagents which associated with a halogen bridge, or it can form this one as well. So all these species are in a Sleng equilibrium. Now the question comes that we have learned about that once you are forming a Grignard reagent, what is happening is going through a single electron transfer. So is there any evidence for that? This, one important evidence comes from that. If you start with this corresponding cyclopropyl bromide, which is 99% E, means it's chiral compound. With now, if you treat with the magnesium and then CO2, once it is forming the corresponding carboxylic acid, what we found it that you are getting first of all a mixture of, so you started with S, now you are getting a mixture of S plus R, and you are seeing that in case of ether your is 20% E, THF 19% E. What is happening here? You are seeing a very poor E. That means there is a racemization is happening, and that racemization is does not matter with solvent, temperature, reaction time, whatever you, or the magnesium purity, whatever you change, you does not able to change this scenario, that you cannot able to. So that is means what is happening, you are losing this stereochemistry once you form the Grignard reagent. Now we try to understand what is happening. I think one of the important aspect, as I told you before, it is going through radical, and now once it is forming a radical, now it can can have a inversion, so it can go to the, I am going to show you that structure in a minute. So before that I am going to tell you the one important question, why partial retention. Of course we know if there is a formation of a radical intermediate, there is a racemization, we understand, but the question comes why there is a partial retention. If you see in the previous slide, we are still seeing some 20% E, why not just 50-50. What they are saying that once this Grignard is formation is happening, there is in the reaction medium there could be some unreacted optically pure starting material. So this Grignard can now, so there could be a this Grignard can react with this corresponding bromide. This magnesium bromide can react with this corresponding bromide too, so there will be transfer of Grignard. So that's how there is, if there is some optically pure remain, then that can form Grignard from this corresponding Grignard reagent. That's how the sum of the optical purity will be maintained there with the most of the racemic material which you are forming. So there will be majorly a racemic material which you are forming. With that you will see some optically pure. Okay, because why it is happening, as I am telling you, there will be some unreacted optically pure which can react with this one to form this Grignard, which can be trapped with the CO2. That's why you are seeing some 20% E in the product. So we try to now explain you why this is happening. If you go back to the radical chemistry, then you can see there, if you treat with this particular compound with tributyl anhydride and AIBN. If you remember, I taught in the radical chemistry, AIBN under heating it is going to generate a radical which can go for a hydrogen atom transfer to generate a tin radical which can cleave this carbon bromine bond to generate a radical species, correct? So now once it is forming a radical species, at the time what is happening, your stereochemistry getting lost. Okay, that's how you are ending up getting a racemic mixture, which you can see here clearly from, there is another example here from this chiral compound. Once you treat with the butyl tributyl anhydride and AIBN, what is happening here, there is inversion happening, as I was mentioning in the previous slide. You can see this radical can go for inversion, it can be in this site or it can be on the other side. So very similar thing you can think about for cyclopropane. It can have a scenario like this. So you can have a radical like this, or you can have a structure where CH3 is here and your radical will be this side. If these are in equilibrium between this and this, if these two things are in equilibrium, formation of this, and if it is, then what is going to happen from this, both the intermediate, there will be a hydrogen transfer going to happen. So once there is a hydrogen transfer is happening from intermediate formation of this radical A or this species B, then it can form this racemic product. So that is happening here in this particular compound also. You are seeing that it is losing the stereochemistry if you treat with the tributyl anhydride and AIBN. But I think if you remember, I talk about in case of organolithium reagent, once you are generating this anion, here you actually retain the stereochemistry, because this corresponding anion which is going to form is configurationally stable. Okay, I think I have already talked about that it cannot participate in the inversion because it cannot achieve the planarity, because that has to achieve for going to the inversion to happen. So now I'm going to start with the alkyl one first, that if you take a alkyl iodide and magnesium and dry ether, you will end up getting the CH3 magnesium iodide. Okay, in general, if you make this Grignard reagent, I think I'm going to come back to the another class where I'm going to teach you how you titrate it. Suppose you make in the solution, now you have to find out what is the molarity of it. Okay, we generally use, sometimes we used the iodine as a titrating agent, but I'm going to teach you some other reagent. So what is going to happen? Once you take iodine and the corresponding CH3 magnesium iodide, what is going to happen? This Grignard reagent going to react with I2 and it is going to consume the iodine. So from there you can see how much iodine got consumed, and you can find the amount of iodine got consumed, and from that we found amount of Grignard reagent form, and from that you can find out the concentration. Okay, so I'm going to take a separate class. So there are other methods as well for organolithium titration, so I'll come back to that discussion later. So what is happening here? Again, I think we are trying to explain you the very similar single electron transfer mechanism here. Okay, so here the similar thing happening, magnesium is giving electron and formation of this CH3 radical, and that's how it is forming the corresponding Grignard. Again, it could be ethyl bromide, very similar to methyl to form the Grignard. It could be a corresponding cyclohexyl bromide. So that means we are saying that there is a primary, then there is a secondary. Okay, again very similarly you can see here that will form the secondary radical. So of course if it is a secondary, the reaction rate will be little bit faster because you are forming a stable radical here. Now if you treat with the aryl bromide, of course it is going to, in case of aryl bromide or aryl iodide, if you treat with magnesium and diethyl ether, it is going to form the corresponding Grignard, but at the same time what is going to happen, it can also form some sort of a dimer, some sort of Woods coupling going to happen, or it can also able to take a proton. Okay, as you can see, these are indication that so this is going through via a hydrogen atom transfer. I think I taught you that if you have a aryl radical, it can go for a hydrogen atom transfer from a solvent to convert to here H. Okay. And again I think that radical mechanism which you are talking, we can have another proof here, that if you have a aryl bromide and with this, so if you have this vinyl group, then it is going to participate in a intramolecular. I think I taught you guys that a 5-exo, it will be trig. So 5-exo trig cyclization going to happen. So that's how you not only get this Grignard reagent as a product, you also end up getting some of the product these cyclized compounds. Why? Because formation of this radical which can add here to the corresponding olefin here, to the 5-exo trig, it will form this one, then it can form the, finally it will form the corresponding Grignard reagent. Again the reactivity order is, if you have corresponding iodo versus bromo versus chloro. If you see, most of the time I am saying iodo and bromo, because that two alkyl halide or aryl halides are mostly used. You will see sometime aryl chloride or also used, or alkyl chlorides are also used, but you will find very rarely if the corresponding fluoride is used for this reaction. Again, if you have this corresponding alkyl versus benzyl, they are aryl, then the alkyl reaction rate is much faster corresponding compared to the vinyl or the aryl halides. Okay. Again, I think you can see there is a order which is given here. Okay. So you can see again the 1 degree versus the 2 degree, then cycloalkyl, tertiary, aromatic. Okay. So these are the different orders in what is follows for the formation of the Grignard reagent. As I mentioned, once you are forming this type of Grignard reagent RMGX, you have to understand very similar to the RLI. I think I taught you that it can act as a base or it can act as a nucleophile. Okay, that is the important thing here. That means you have a R actually as a minus. So if it is a minus, you can think about from a methane, it is forming finally. If once you make a Grignard, you are literally forming this some sort of a CH3 minus. So you can think about CH3 magnesium X as a equivalent to CH3 minus, correct? Once you form it, it can act as a strong base as well as a strong nucleophile. That means it can abstract a proton from here. If you have a alkyne, in that case what is going to happen, if you take a Grignard reagent, it is going to abstract this CH proton, okay, to form this corresponding alkynyl Grignard reagent. I am going to come back to that discussion also. Here I think you can see in this page, if you use a ethyl magnesium bromide, diethyl ether, then what is going to happen here? These are the acidic proton here in the alkyne that is getting abstracted here first to form this corresponding alkanyl Grignard reagent here. Okay, if you have a phenylacetylene here, you use ethyl magnesium bromide in diethyl ether, then this is going to abstract this proton here in the alkyne to form this corresponding alkanyl Grignard reagent. So what we have learned, that we have learned you can make alkyl Grignard bromide, you can make some aryl Grignards from the aryl bromide and iodide, and if you have an alkyne, then you don't have to form the start from corresponding iodo or bromo. You can directly start from the corresponding alkyne, and you can by a deprotonation using another Grignard reagent, another alkyl Grignard reagent, you can able to make this corresponding alkanyl Grignard reagent. So till now what I was talking about this different aryl and alkyl Grignard reagent. One of the important thing I should mention that when you are forming a Grignard reagent, compared to organolithium, there are methods where you can keep the the functional group. Suppose in your molecule you have a functional group. Here we have an example, we have a functional group and we have a iodo-bromo. So now the question comes, if you treat with organolithium, as organolithiums are very reactive, once you go for a metal halogen exchange, then there is a chance that this functional group also going to get attacked. Of course, we have learned that if you go to very low temperature like minus 100 degrees Celsius, then it is possible to control. We have shown you some example in the class. But here we are talking about that if you use isopropyl magnesium chloride. So this reagent also commercially available. If you get isopropyl magnesium chloride, now you can able to go for this metal halogen exchange. So here again you can see the metal halogen exchange is happening at minus 40 degrees. Sometimes this can be done at minus 25 degrees, depending on the functional group. And you can able to cleanly convert this corresponding carbon iodine bond to carbon magnesium chloride. So one of the thing is, in this particular reaction always you have to start with corresponding iodide, mostly with corresponding iodo. So then what is happened, the isopropyl magnesium chloride can participate in the metal halogen exchange and it will not interact or react. As you can see, it is a isopropyl group is here. So that's why what is going to happen, as this is a bulkier group, okay, this Grignard is even less reactive, so that's why it is going to participate in a transmetallation to introduce the magnesium chloride here. You can see there are several different groups, like in this particular compound you have a nitro and cyano. It still works fine. I think Nochel groups from Germany actually developed this strategy. And there you have a nitro group here, of course methoxy will be fine anyway, but here it is important, you have a nitro, you have a ester, correct? So in this case, if you try to with the organolithium, I am sure this ester will get attacked. Here you have a two nitro groups still getting survived. Again there is an example, again you have a ester here and you have iodide. So now using isopropyl magnesium chloride at minus 20 degree, in 30 minutes only this metal halogen exchange was done to form this corresponding magnesium bromide. Okay. So this is showing the uniqueness of this reagent, that isopropyl magnesium bromide can be used for metal halogen exchange to get to the corresponding Grignard reagent, keeping the functional group intact. Again there is an example here, you can able to also form this corresponding Grignard reagent. Not only this is this particular reagent only works for sp2 corresponding iodide, like if you have something like corresponding sp3, like if you have a cyclopropyl group and you have a bromide, you have a so actually this one started from the corresponding the dibromide. So what is going to happen, I think this could be chloride or the bromide depending on the the group you have. So you can see it is actually leaving a ester unreacted. Okay, it can also works with the vinyl system. Here you have a ketone and you have a corresponding you have made the corresponding magnesium chloride using this isopropyl magnesium bromide. So depend on the isopropyl you have, it could be isopropyl magnesium chloride or bromide. I think both is works for this type of reaction. Okay. Again some more example here, in this particular heterocycle here this corresponding carbon bromine bond was replaced. So there is a metal halogen exchange happened to form this corresponding magnesium chloride. Then in case of the heterocyclic ring, where you see that here also the metal halogen exchange is possible to get to this corresponding Grignard reagent. Again, you can see sometimes the reaction can be go up to 25 degrees Celsius without seeing any other side reaction, which will be difficult if you try to do with organolithium. Because organolithium you have to always use very low temperatures. Here you have two bromo here, and if you use this corresponding isopropyl magnesium bromide at -5 degrees, you can selectively go for a metal halogen exchange to get to this corresponding Grignard reagent. Now we are going to talk about that in case of this magnesium turning, as I was mentioning you guys, that there is a magnesium oxide layer. So that's why this reaction is slower. It took some time to form this corresponding Grignard reagent. So there is a activated magnesium turnings where you don't have the magnesium oxide. They started from the magnesium chloride using lithium and naphthalene, which can give you an electron source. If you remember, they can generate a compound called Rique magnesium. So this Rique magnesium is, or we are going to talk about this similar thing in the Rique zinc. So these are a very reactive magnesium species. Okay, it is just ready to react. So these type of species are very fast going to react with to corresponding alkyl chloride to form corresponding Grignard reagent. If you think about, if you have a tertiary alkyl halides, so think about here what is happening. Now the corresponding alkyl chloride, which was telling you is going to be less reactive, corresponding to the bromide and iodide, now it can participate in the Grignard reaction formation. Again, here is an example here. Corresponding bromide can be also converted to the corresponding Grignard reagent. As I was mentioning you, as it is going through a radical intermediate, so it might going to lose the stereochemistry. That means you might end up getting to the product which will be either cis or trans. So you end up getting a mixture of the product. That is the problem with the Grignard reagent, which you see if you do the same reaction, go for corresponding vinyl lithium and do the reaction, I can guarantee you this will be end up giving you the corresponding COOH. Okay. Again, I think I have already explained you why that is happening for carbon ion versus the radical chemistry. Again, this reaction has to be done under inert atmosphere. You don't want oxygen to be present. If oxygen is present, it is going to react with oxygen, very similar to the corresponding organolithium. It is going to form the corresponding alcohol after once you treat with H3O+. It can also react with the corresponding aldehyde if you have a formaldehyde, or if you have any type of course if you have water or acid or amine, it is going to go for a proton abstraction. And if you have a formaldehyde, we are going to discuss this part. In the next class, we are going to discuss more details about the reaction of the Grignard reagent with the carbonyl group. In generally, what is happened, there is a 6-member tangent formation happens. So again, this depend on what type of Grignard you are using. Okay, if you have a smaller size Grignard, you can think about this type of 6-member tangent state. Why? Because you can see here 2 equivalent of Grignard is actually participating. One of the Grignard reagent acting as a Lewis acid to activate this oxygen, or to form a coordinate with the oxygen to activate the carbonyl group. Once it acts as a Lewis acid, it can activate the carbonyl group. So now the nucleophile attack going to happen from the another Grignard reagent. So through a 6-member tangent state, it can going to form the corresponding alcohol like OMgX, which will convert to the corresponding alcohol after treat with water, and there will be one Grignard will come out. So what is going to happen? One of them only getting reacted to the product, and one equivalent is coming back to the mechanism to start the next reaction. So in this part, I already told you that what is the definition of the Grignard reagent, how to prepare them, what are the reactivity, why different type of solvents are used. You have seen mostly THF and diethyl ether are used, and I talk about the different structure, and then what are the different mechanism. I talk about the radical mechanism. I give you some evidence to justify that. In the next class, I am going to talk about the different reaction of Grignard reagent. Again, these are the references you can follow. And again, thank you for coming to the class, and I am going to see you guys in the next class. Thank you.